Okay, so hi and welcome everyone to my talk of our latest submission, the Uncanny Valley Exploring Adversarial Robustness from a Flatness perspective. So this is joint work with Lina, Nils, and Michael. Lina and Michael are both also here in this talk. So we're going to talk about adversarial robustness and flatness. Okay, so first, I mean, by now, I guess everybody saw adversarial examples at some point, but just to give a refresher, we have a clean image. And our classifier says that this is a panda, and this is also correct. Then we take or carefully craft some adversarial noise via gradient descent on the image instead of the weights. And then if we add this noise to our image, suddenly our classifier says given. And this is, let's say, a rather old problem. And there has been a lot of research, but it's still open. So although there has been significant progress, people are still a bit puzzled on how to solve this. And what we asked essentially is, can we analyze the flatness and how can it help? So what do we mean with flatness? Initially, this was introduced by Hochreiter and Schmidt, who were already in 1995. And this is a quote from the original paper. So what they mean is that you have a large region in the weight space with the property that each weight vector from that region leads to a similar small error. And intuitively, it's that if you have, essentially, if you start wiggling your weight and it doesn't change much, then the intuition was that, okay, you're now in a generalization area of your loss surface, and then you get good test accuracy. Okay, so, and this intuition also holds true in a benign setting. So Michael and Lara, they had a paper where they showed empirically first, or also empirically, that the flatness of your loss surface strongly correlates with the generalization capabilities of your neural network. And not only like empirically, but they also prove that you can show that given their relative flatness measure that I'm going to introduce shortly, there is a strong connection there. Okay, what do we mean with generalization here? So everybody has the intuition what it means. So the difference is, what it is the difference between the error on the overall distribution if you had access to really the data generating process minus the empirical distribution, what we really measured. So what they showed is that you can decompose this into a global and a local property, whereas this global property corresponds to something called epsilon representativeness, more or less that the data you have is sufficient to really learn something. So it really resembles your data distribution. While this local property is what I call feature robustness, and this is what then really corresponds to the flatness. And then the next question is, how would you assess that this loss surface with respect to the weights of the neural network is really flat? Okay, there is a whole plethora of what I call these empirical ways of measuring this. Here in this formula, you first assess the loss with respect to the weights you're currently at. And then you start sampling in your neighborhood of these weights. In this case, it's some normal distribution. And then the intuition is that if you are at a certain position and I sample points and the difference between these points is minimal, then it's actually flat. And there are also this worst case flatness or measure where you take an adversarial step in the weight space and then measure the difference. Okay, now, although this is intuitive and quite nice, the problem is that if you want to do proofs with that, it gets a bit hard. And also, let's say from an analytical perspective, you can assess the local property of flatness via the Hessian, so the eigenvalues of the Hessian. But really computing the eigenvalues of the Hessian, especially for a complete network, is also completely infeasible. So instead, you take the trace of the Hessian, which then corresponds to the sum of the eigenvalues, and then you get some idea of how these eigenvalues look. Because if it's now really zero, then you very, very high probability intuitively it's also it's flat there. Okay, then here there's also the second term where you normalize by the weights. This for us is not too interesting, but for completeness, this is such that this measure is invariant under certain changes of your weights. And if you express them in a different, what's it called? Yeah, different parameterization. Okay. Then what they also showed is that it is sufficient to measure this flatness in the penultimate layer, and it's also what we do. And if you additionally constrain yourself to the cross entropy loss, it takes a very nice form. Because technically, the very last layer is just a logistic regression, and you can easily derive the Hessian analytically, and it's very fast to compute. And still very insightful. Okay. So why would we even believe that there is a nice connection for adversarial robustness? Because flatness measures changes in the weights, while adversarial examples change the input. So the intuition is, or the main idea is that if you have these changes in the input, you will at later layers equivalently express them as changes in your weights. And then the idea is that if I change my input a bit, my weight also changes just a bit, but since it's flat, it doesn't matter. Okay, then here a very simplified derivation. So we have, in this case, let's say, image, and then a little perturbation of this image we added. And that's then what we, in this case, is our adversarial example. Okay, and if we now do some very easy rewritings, we will end up that we can define this W hat, and we're back at this clean example. And if it's now flat, this perturbation just didn't change the loss, and hence also similar prediction, everything is fine. So if this were really the case, right, then we could guarantee if it's flat, we also don't have adversarial examples, but in practice, of course, right, it's quite easy to find adversarial examples. So the next step why we believe that this, or where this intuition comes in, that if we now look at this definition that has been floating around since 2014, of an adversarial examples, it's defined as an optimization objective, where you search the minimal perturbation such that your label flips, and then this perturbation plus your image, this X, is then what they call an adversarial example. So, but having an optimization objective for a definition is also not particularly handy, and it doesn't, and to make certain things a bit nice and reordering them, and also making certain assumptions that they make in this definition explicit, we let's say adapted the definition a bit, but it's still equivalent. Okay, so what you have now, you have this distribution over your probability, over your images and your labels, right? Now, given a distance function and two thresholds, we call an adversarial example eta for an image X if the distance is smaller than this delta, right? Standard adversarial examples, what you here have in this part. And then what we want is that even under the small changes, our loss changes a lot. And if this is the case, we call this an adversarial example. And I mean, if your loss changed enough, then you flipped the prediction, and that's then where we're back at this initial definition. But if you write it out like this, it becomes very apparent that it's more or less, I mean, this is not really an epsilon delta criterion for smoothness, but it kind of has the same vibe. And therefore, you also can have this intuition that flatness may help there. So, and also there is empirical evidence that this indeed helps. So here, this is a plot from a different paper, where on the left, the authors plot the loss on the adversarial examples. On the right, these are various adversarially trained models. Back at that time, let's say there were so many different versions. After all, more or less, they do the same. I mean, they just inject adversarial examples during the training, and that's then how they achieve more robust classifiers. And on the bottom, they then evaluate one of these empirical measures. Like this is the average case I showed you. They just start sampling in this area, and what they find is that indeed, if these models achieve a lower robust test loss, they really and are also more flat. And that's then this let's say empirical evidence and the justification for this analysis. Good. Our setup is a bit different. We start with a model. In our case, initially we start with a right ResNet. We train it on Cypher 10. Then we do an iterative attack, PGD, where we allow a budget like this delta, 8/255, and we constrain with respect to L infinity. Intuitively, this means that you can change each pixel value by 8, and then you do this for 10 iterations. So this is sufficient to get basically every classifier of like wide resonant, dense net, or whatever I'm going to show later to get 0% accuracy. Important to note, we do not stop the attack. So for this, we get a whole trajectory of adversarial examples. I mean, this is technically what we would look at, right? I mean, it's imperceptible, nothing will change, but the model will behave drastically different. Now, here comes a bit of how our setup is a bit different, because at each of these iteration steps, you get something like an adversarial distribution per step. Now, we take this data distribution, and then there we start evaluating our flatness. So instead of only varying the weights, we also vary the data distribution. So we go to this data distribution, we create that, and then we start wiggling our weights and check, like, how does the flatness or the loss surface look there? Okay, now, bit of this, like, if you buy into this intuition that, or what I also showed you earlier, is that if you're in this, let's say, flatter area, you should also generalize better. And the first thing that we measured is obviously the loss. And as expected, per attack iteration, the loss goes up. So on the bottom, on the x-axis, we plot the attack iteration, and y, the loss. Okay. So what we really wanted to see is kind of like this. So here we plot the relative sharpness. Just prior to that, I was talking about flatness. Essentially, it's the same thing, just one minus, right? And what you see is that what we hope to see is that as the attack iterations go up, also, let's say, the relative sharpness goes up. And that's why I call them the curves that we deserve, because if this were the case, like, our theory would be very neat, and we could show pretty nicely that you need this flatness, and our bound would work out perfectly, and everything would be nice. But what we observed in practice is very different. So obviously the loss goes up, but this is the curves that we get. Instead of things getting sharper, we go into suddenly this very, very flat region as we progress the attack. And this point also splits more or less the contribution that we have is, for this, we have this bound. So in this small area, you can, based on flatness, give a guarantee that you won't find an adversarial example. But given this phenomenon that we had, it is obviously not the case globally. Okay, and that's this area that we called an uncanny valley, because when we really saw it, we were like, okay, that is really not how it's supposed to look. Okay, for completeness, I want to show this bound, because there was a lot of work to get there. The main gist is that given a certain change of loss, we can really guarantee that in this delta, which takes this form, there won't be an adversarial example. And important to mention here is that it is inversely proportional to this sharpness measure or this flatness measure. So if it's 0, our delta will be very big, and vice versa, if it's large, we cannot. So if it really captures the intuition that we have. Good. So then, as teased above, we did not only look at wide resonant, but we evaluated the whole plethora of models. So resonant, VGG, densenet, and some others I didn't bother putting it on the slides because it is really exactly the same. So initially for Cypher 10, it goes up, and then it goes to this very flat region while the loss increases. In contrast, here for Cypher 100, initially don't start in that flat region, but you still go to 0 as the attack progresses, which is, yeah, rather unintuitive from our perspective, at least. So we also find them in LLMs, because by now a lot of people are looking in these jailbreak attacks, where from an adversarial example perspective, more or less, these are targeted attacks such that you have certain starting of your prompt. So the attack that we looked at is GCG, so it just finds a certain prefix to your initial prompt such that you get a certain output. And here the trend is not as nice. So this is just, again, the average over all attack iterations. And as you can see, like it first of all takes like way more iterations. And if you look here, you could argue that initially it goes up, right? I mean, this is obvious, but then it goes down very timidly. While if we now look at specific instances of examples and attacks, we will find that indeed there's a similar phenomenon. So it's not as pronounced as for these nice curves on the images, but still, initially it goes up and then goes down, which showcases that this is kind of, let's say, present in various architectures and not limited to only images. But here, what we hope for is that as now the attacks get stronger and stronger, you will see the same phenomenon, but potentially not as smooth because factually just you're optimizing over discrete space and this is just harder. Okay. What we also wanted to make sure is that are we running in circles? So, or are we really now going further and further away from our initial position? To do this, we measured both the distance in the input space, which I plot on the top, and the distance in the feature space. By feature space, I mean this penultimate feature representation. And as you can see is that with progressing attack iteration, all your distance increases and you really don't walk back. And in feature space, the same phenomenon. What we found quite interesting when looking at these plots is that here for the cosine dissimilarity, a very small change in the angle will translate to a very large change in the angle in the feature representation. And this also goes hand in hand to what people are currently observing in all sorts of domains, that what really makes up these representations is more or less how they're oriented in space according to the angle, not particular to the distance. Just a side note. Okay, then next we checked how does it look in earlier layers, and I would argue this looks really exactly the same. So we don't measure in the penultimate layer, but also in layers before, where we cannot compute it analytically anymore, but still there's like sufficiently strong approximation. And what you see is that all what changes if I go to these earlier layers is just the magnitude, but the general shape stays really the same. So it really justifies also that it's sufficient to look at this penultimate layer. Good. What we also want to know is this actionable what we're seeing? So is this just observation which is nice, but you can't do anything with it? For that, we checked whether we can detect adversarial examples using this flatness measure. So if you look at the trace of the session, you write it a bit differently. Then for each of these parts of the sum, we have one feature, and then we get this feature vector. So next we generate like a complete data set of these adversarial examples, like in a 50-50 split, generate these feature vectors, and then train a decision tree on these features. And let's say now in terms of storytelling, right, this is a bit nicer to tell it like this, but initially really started by exploring in more, let's say, analytic style on how this flatness really looks. But the long story short is that you can, with this approach, detect adversarial examples with 95% accuracy. And if you really look at this decision tree, you see, I mean, factually, it's mostly splitting on zeros. But still, like 95% accuracy is well above random. And for LLMs, I would argue that here I also can make the point that for these GCG attacks, you can detect it quite easily, whether it's getting attacked or not. Okay, now I want to give a bit of intuition on what we think is in this uncanny valley and what is the shape or what is going on there. And these are preliminary results. Like this is not what we have in the paper currently, but we plan to incorporate it quite soon and update the submission, or on arXiv at least. So here, as you see, image credit goes to Michael. He generated this with some model, I don't know, but it really displays what we believe what we have there is that initially you are in this region here on the top right? And you have still a bit of curvature, but during the adversarial attack, you find this path to this broad uncanny valley, which means that you have like these very dense areas of these adversarial examples. And if we now look at this and try to test this hypothesis, so again, run these attacks, then instead of just, let's say, taking this particular adversarial examples, we now start sampling in this neighborhood using a normal distribution and around this adversarial examples and with a variance parameter, which is chosen such that the distance is limited. So it will be perceptible, but it's still not that you are at complete noise initially. And the curves that we get is here I plot here on the y-axis the infinity distance and here on the y the sharpness. So initially, it shows our intuition is going at least in the right direction, that it is very sharp. It's very flat here, up to a point of 0.1. Just to give a bit of a, say, the angle as a point here. So the PGD attack perturbs till 0.0314, which is roughly 0. So you really see that it's way, way broader than the attack actually is. So it's a nice area. But still, if you look at the right, the loss decays, although it looks kind of very flat. And this is also true. If you look at these values, it's not exactly 0, but still very, very flat. So what I would suggest is more like, okay, you are in this very flat region, but still there is some curvature which could leave you back. And ultimately, you will go back. Also, what's interesting is that the sharpness goes up and up, right? While your loss gets lower and lower. Okay. Then, our next intuition is that, and we are not the first ones to really have this idea. I just didn't found the paper that I have in mind there, but these are these weird wormholes that you go to. So these big blind spots of your data. And as you can see here, like many of them, all these blink spots are these wormholes to these uncanny valleys. So, and to test this, it's a bit more, let's say, a bit harder. So what I'm going to show next is like the ideas that we have, and there would be very looking forward to the discussion and listen to the ideas that you have. Is that first step was just to do noise interpolation. There it's known that you will at some point just flip the label because you have pure noise, but still it's not clear on how the sharpness, let's say, changes on this trajectory. And this looks something like this. So again, on the x-axis, I plot the L infinity distance and y-axis the sharpness. And as you, let's say, progress to more or less pure noise, your sharpness goes up with a little bump here around 0.4, while, okay, the loss increases and then goes down a bit. But still, it's not really flat as we saw for the adversarial attacks. The next idea is what we want to do is kind of, or also looking a bit ahead, what we want a nice mathematical description of how we can walk on the manifold and go to these like these areas which are properly covered by our data and these blind spots, but not, let's say, because there are these works that do, they learn essentially this noise distribution of these adversarial attacks, and you have them in again or something like this, and you can create adversarial examples, but it's not what we want because it's not a nice like mathematical description that you can look at. So the idea is that we compute the span and the kernel of the data. I mean, span maybe, kernel we can't. So what we do is that we take a singular value decomposition of our data set, we split it according to our singular values. And to have this notion that we have this fixed point or this direction in our data where we can either go to these uncanny valleys or to these, let's say, proper areas of our manifold, we fix one point and then we interpolate like every image to either the span or the kernel, and then plot the sharpness on this path. And here I'm not plotting their infinity distance, but rather just the iterations of the interpolation. So these what I call for now, or we call for now, manifold directions. And what you see is that as the iterations progress, the sharpness just goes nicely up. So it really kind of gives you this idea that I go more or less on this manifold instead of just to these uncanny values. While if we purely plot the lower singular values, it's a bit more of what we want. So we can now go to, it kind of resembles a bit to what we see in the noise, right? But it goes way to these non-sharp areas, but still it's not comparable, but it kind of indicates that having a nice description of these blind spots of your data would give you a proper, let's say, understanding of what these adversarial directions really are. And that's, okay, what I'm also looking forward to discuss next, but to look a bit further of what you see here, because if you go really to these very end blind spots, right, it still just gets sharper and sharper. To look at this, I just plotted the images. So here at this peak, there is already very visible noise. Here you barely can see that this is supposed to be a ship. And here's just noise. There's nothing anymore, just pure noise. And here, let's say if you have any ideas on how to improve it, yeah, we would really appreciate it. Okay, to come to an end. What we saw is that adversarial examples are still not really solved or understood. So what we hope for is that this relative flatness measure or flatness can help us to understand or circumvent these adversarial examples to a certain extent. But what we saw is that this is not completely possible. We can, in a certain neighborhood, we can really show that there is this bound, and depending on, you really need a flat area to do this, but it doesn't capture that globally, that you get a globally adversarially robust model. And the problem that we're having is this uncanny valley. So you get these weird regions where our, let's say, we technically have a large bound, right? But yeah, it's not adversarially robust there. And the intuition is that it's kind of this broad valley and you have these wormholes to go there. Okay, then thanks for your time. And now I'm looking forward to the discussion.